All right, next is problem three. And so problem three is going to involve application of the Maxwell-Boltzmann distribution. And so I won't spend too much time on this, only because we've spent so much time with problem one and two on unit conversions that we'll talk about the Maxwell-Boltzmann distribution, what equation to use. But I'm going to leave the number crunching and the unit conversion that this problem is going to ask you to do up to you. Okay, but so looking at problem three. So at 0.01 degrees C and 611.73 pascals, water coexists in three phases: liquid, solid, and vapor. And we're asked to calculate the mean thermal velocity in each of the three phases in meters per second, kilometers per hour, and miles per hour. So three different sets of units. And then we're going to calculate mean translational kinetic energy and translational kinetic energy. Okay, so just looking at the first part, so the thing to keep in mind from our Maxwell-Boltzmann distribution is that if I have two phases of coexistence, in this case I have three phases of coexistence. So if I'm at the triple point of water and I have a solid in equilibrium with a liquid in equilibrium with a vapor, those three phases are all going to be at the same temperature. So a key feature of the Maxwell-Boltzmann distribution is that my average velocity is only going to be a function of mass and temperature. Okay, so the mass of my water molecules is exactly the same in all three phases. Water is water, or a water molecule is a water molecule, and the temperature is exactly the same. So regardless of if we're dealing with a solid, liquid, or gas, the mean velocity of water in all three phases is going to be exactly the same, right? And this might not be what intuition told you initially, right? You think about gas molecules moving about freely. Molecules are really far apart, and so my water molecules have a really far distance they can travel before colliding to another water molecule. Liquid phase, right? We're still moving about freely, but our molecules are much closer together. And then a solid, it's like, oh, I'm frozen. I'm on a lattice point. But it's again, Maxwell-Boltzmann distribution tells us that our velocity is only a function of mass and temperature. So our water molecules all have the same mass in all three phases, and all three phases are at the same temperature. So in actuality, the mean velocity of all three of those molecules is exactly the same, or the molecules in all three phases is exactly the same. Okay, and so how would I calculate that? So I'm going to go over to the textbook as it is online. All right, and so here's the Maxwell-Boltzmann distribution. So here's our distribution of velocities for our system, a given mass and temperature. Okay, and so the mean velocity is given by this equation here, right? So I'd use V bar is equal to 8 kBt over pi times m to the 1/2. All right, now just a note, as you do the actual calculations, you can do some tweaking. So Kb is essentially my molecular gas constant, right? So my gas constant's R is 8.314 joules per mole Kelvin. Well, Kb, our Boltzmann constant, is our gas constant, but instead of being on a per mole basis, we want it on a per molecule basis. Well, how do we get from then R to Kb? Avogadro's number, right? Which tells us how many molecules are in a mole, right? And we can write that out on the next slide. So essentially, we're going to want to use V bar, all right? And if I use V bar, here, right? If I just use SI units, it'll get me meters per second, and then I can go and perform said unit conversion, right? But key is the mean translational velocity is going to be the same in all three phases. So it doesn't matter that I'm dealing with liquid, vapor, or solid water. Those molecules are all going to have the same average velocity. Okay, cool. Yeah, and then the other thing to note is when you calculate the speeds or the average velocities in miles per hour, you'll find that molecules are actually moving pretty fast. Okay, but okay, so I'm so especially in C, when I'm looking at, say, oxygen and air, right? Oxygen is moving fast, right, in the air surrounding me. How come I'm not getting beat up? How come I'm not going home at night with black and blue marks? Well, it's very fortunate for us that molecule of oxygen weighs very little. And so, all is good. So cool. Okay, now I just want to, so that's, the equation I'd use for A. We'll come back to some masses in a second. Then C and D, or B and C, we're asked for mean translational kinetic energy. Okay, remember when I think about kinetic energy, all right, K's, 1/2 mv squared. Okay, and so what I need then isn't my average, it's not my average velocity I squared, but I'd want to calculate the expectation of my velocity squared from my velocity distribution, not the expectation value of my velocity and then squared that. And so all I mean by that is they also give you, v bar or bar, v squared bar, so the expectation value of my velocity squared, which is 3 kbt over m, which is different than this quantity squared. All right, so when calculating my kinetic energy, K is 1/2 mv squared, I would use, v squared bar, the expectation value of my velocity squared. Okay. Now, just, one note I want to make for when you actually do these calculations is, I typically don't remember a value of Kb. Okay, Kb is just my molecular gas constant. But I do remember my molar gas constant, R, is 8.314 joules per mole Kelvin. Okay. Then I remember Avogadro's number, right? And Avo is equal to 6.022 times 10 to the 23, right? It technically has units of inverse moles, right? And so what that tells me is how many molecules, right, I have in a mole. How many molecules make up a mole? Okay, so R is my molar gas constant. Okay, Kb is my molecular gas constant. So how do I go from one to the other? Well, Kb, okay, then it's going to be defined as R divided by NAVO, right? Because NAVO has units of inverse moles. So if I divide R by NAVO, so 1 over NAVO has units of mole. Units of moles cancel. All right. So R divided by NAVO gives me my molecular gas constant, which is just going to have units of joules per Kelvin. Okay. And that's all there is to it. If you wanted to calculate the mass of something, okay. So I know the molecular weight of water, for example. The molecular weight of water is 18 grams per mole. Okay, so if I wanted to know what's the mass of a water molecule, well, the relevant conversion factor of interest is just going to be NAVO. Okay, so if I wanted to know the mass of a water molecule, okay, it's going to be my molecular weight, okay, which is in grams per mole. Okay, and so then I would divide by NAVO, because 1 over NAVO is going to have units of moles. Okay, remember NAVO tells me how many molecules in a mole. So if a mole of water weighs 18 grams, and I divide by NAVO, okay, how many molecules are present in a mole, then what it's going to do is it's going to give me mass, in this case, in units of grams. It's going to give me the mass of a molecule of water. Okay, and just looking, molecular weight of waters, in order 10, and magnitude or N Avogadro's on the order of 10 to the 23. So 10 to the 1 divided by 10 to the 23. All right, so molecular weight is going to be what? On the order of 10 times, or 1 times 10 to the negative 22. All right, so the mass in grams of a water molecule is really small. All right, and so again, this idea of molecules are traveling really fast around us, but they don't hurt us. Right, when I'm swimming, I'm not getting beat up by water in the pool because it weighs so little. Okay, but I'm not going to go through all of the calculations since we've just did 2 big conversion problems. But key is in A, you can use the equation that's given for the average velocity, or the expectation value of my velocity from the given velocity distribution. And then in B, when using kinetic energy, I want v bar squared, not v bar squared, right? I want v squared bar, the expectation value of my velocity squared. Okay, but hopefully that helps. All right, if you have any questions from there, let me know. And again, R and NAVO, right? It's R over NAVO gives you Kb, my molecular gas constant. And if you want to get, a mass of a molecule, knowing molecular weight, all right, you would just divide by NAVO. Okay, so hopefully that helps. Any questions? Let me know.